momentum and impulse. I know you guys are tired. You went through a whole math session. It's been a long day. But I only have so much time with you guys, so I'm going to keep going. In terms of momentum and impulse, you guys must remember, please, that we are again dealing with vectors. A lot of you forgot about that, and because of that, in the last question, you lost marks. So in this case, the first questions are pretty obvious, and you guys tend to be okay with the definition. State the law of conservation of momentum. Remember the word total. And grade 12s, you may not exchange the word isolated system with closed system. The words do not mean the same things. In physics, we use the term isolated system. Yes?
Ma'am, let's say your teacher has always told you that you can use that.
Okay guys, that's a very fair question. It's a very fair question. Your question is, what if your teacher told you that you can interchange the words? Okay. Excuse me? Alright, guys, this is what I can say, right? There's lots of things that you guys are going to see I mentioned, and maybe your teacher didn't tell you or told you you could change them and so on. Like, for example, free body diagrams. I did not know at the beginning of this year that you guys were no longer allowed to draw free body diagrams with the components. Now let's say my learners go to the final exams and they interchange or they include those components. It doesn't matter what I said as the teacher, whoever marks their script is going to take away their marks. Okay, so look, what tends to happen sometimes is that we mark according to how we teach, and maybe your teacher will be lenient because they taught you a certain way. They'll be lenient in the trial exams, which contributes less than 5% of the final mark. But if you repeat the same mistake in your finals, the person marking doesn't know what your teacher taught you. They only know the right way. And they're going to take away the mark. So I don't want to disrespect any teacher. We're all trying. I'm not a perfect teacher myself. And I've been learning over the past few years very, very humbly, because this subject humbles us as much as it does you. Okay. But, so I can't comment on how your teacher will mark if you change the word isolated to closed system. But please learn from what I'm saying. I've taken this from the presentation from the department at the beginning of the year, which says you are no longer allowed to use the term closed system. So please be careful. And if any of you go home to your teachers, to your schools, please don't disrespect your teachers, okay? Just because I'm telling you guys something different. Again, we're all trying to learn on this path called life, okay? Now, you guys have to perform a calculation. And question 4.2. We are okay with that, I think. It's question 4.3 which is a problem. Guys, if you do the following, it says, is the collision between the bulletin block elastic or inelastic? Use a calculation to justify. If any of you start off by doing this, the sum of EK before is equal to the sum of EK after. You're going to get 1 out of 4. Please don't do this anymore. Just like in mathematics, when you are asked to prove something, you cannot start off with the statement. Here, you have to start off by proving whether it is elastic or not. So never equate the two sides. You start off by finding EK before, you plug into it. In a separate calculation, you find EK after, you substitute into it. You then check to see if they are equal. If they are, you state that they are equal. If they are not, you state that they are not equal. And then you come to your conclusion. Please never do this again, I beg you. I have had my group of learners for a long, long time. I've been teaching this for a long, long time, telling them over and over again, you must not do this. And yet I still had learners doing this. Please do not do that in your exam. 1 out of 4 is 25% for this question, and it's not necessary for you guys to lose marks for a question like this. Okay. Then they go on and they speak about a net force. They say that this bullet is now going to hit the block, and it's going to experience a force of 5 newtons down. Grade 12s, if anything slows down, so if I am running and you want to slow me down, you're going to have to apply a force in the opposite direction to my motion. And that force would be a net force acting on my body. Well, it depends on whether or not my feet are still moving, but it will be a force that way, and it will accelerate me that way, even though I'm still trying to move forward. If anything slows down, then its acceleration is in the opposite direction to its motion, and therefore in the opposite direction to its velocity. So in this case, when you had to use this formula, and you substituted the initial final velocity of the bullet, you had to insert your net force in the opposite direction, which in my case, because I have chosen upwards to be positive, when it crashes through the wooden block and slows down and exits on the other side, the net force acting on it, which slows down the bullet, is downwards and therefore negative. So the moral of the story here is momentum and impulse includes vectors. Are there any questions, any problems? May I move on? Okay. Work, energy, and power. This one's my favorites. Every single year I get hundreds of learners, whether it be in the winter school or in class, saying to me, "Ma'am, but how do I know which formula to use? I don't know which one to use." And guys, I struggle to answer the question because in most cases, there will always be more than one formula that you can use. And so these questions are all about you choosing through a process of elimination. So you see, I inserted the pretty picture of the question that you guys had, and then I was like, when I was busy doing this, I was like, but I have absolutely nothing to say about it. So I want to refer you guys instead to the summary booklet. If you go to page number 6 of the summary booklet, page number 6 of the summary booklet, you are going to see one page that lists everything sort of that you need to know about work, energy, and power. Okay? Every single page in that booklet has been created so that you have one page on everything about a topic. My idea when I created it was, if I were a learner at the end of the year and I want to study, what I want to do is recall all the information, leave it alone, and then try it in a problem. So my idea was that you guys can read through everything here. All of the definitions I took from the DBE, the Department Exam Guidelines. So if you're in a government school or an independent school that follows the government syllabus, you can learn these definitions as they are. Okay. But this is what I mean by process of elimination. So the first thing we need to do is distinguish between conservative and non-conservative forces. And in my opinion, the way we define them doesn't help much. When we speak about conservation, when we speak about nature and we want to conserve nature, we're speaking about reserving something, holding on to it, not changing it. We only have so many of this thing and I want it to stay that way. Of course we want, the animals, the rhino to become more, but at minimum, let it not become less. Okay, so conservation is all about keeping something constant. So we say that a conservative force, or examples of conservative forces, are the gravitational force, the elastic force, which you guys don't deal with, which is from a spring, and the electrostatic force, which I've never ever seen in a work energy power question. This might be your year. I hope it's not. Okay. So based on history, I would say you guys must remember the following. If the only force doing work on the system is Fg, then you are dealing with what we call an isolated system. enter the pendulum. If you have a pendulum, where you have this ball that is moving to and fro over and over and over again, a lot of people, if you analyze it very deeply, say it's not only Fg acting on this little bob at the end, this little sphere. We have two forces acting on this little circle ball at the end of the pendulum. The first one is a downwards Fg. And the second one is a tension force, holding it on the string as it moves. But you see, the thing about this tension force, although tension force would and should be defined as a non-conservative force, the fact is that as this pendulum moves through space, or as a little ball moves through space, you see at this instant, it's going to move there. That's where our change in x is going to be. And if you look at the angle between the tension force and the displacement, you'll notice they are perpendicular. So is the tension doing work on the little ball at the end? No. And that is why when you see a pendulum system, we say it is isolated. It's because the only force doing work on the situation is Fg, and Fg is called a conservative force. It's called a conservative force because it conserves mechanical energy. If the mechanical energy is 5 joules, it's going to stay 5 joules if it's only Fg acting on the system. So if I take my pencil case and I say, here's my pencil case a certain height above the ground, and it has a certain, well, let's put it on the ground. Let's start it over here. Okay, certain height above the ground. At this point, I am holding it, so it is not an isolated system, there's an applied force. But as soon as I let go, and I don't want to let go, but imagine it's falling down. As soon as I let go, what happens is that the potential energy is converted into a different form of mechanical energy. What does it become? Kinetic energy. And if it currently has 5 joules of potential energy, just when it hits the ground, it will have 5 joules of kinetic energy. When its height is 0, all of the potential energy that it once had would have been converted into kinetic energy. And since mechanical energy is the sum of kinetic and potential energy, we are seeing that this mechanical energy is conserved. That's a conservative force. If we look at non-conservative forces, taking this thing, what is this called? A table. This thing as the ground, pretend it's the ground. At the moment, what would the mechanical energy of my pencil case be? 0. It's not moving, it's on the ground, it has no height, it's not going anywhere. Assuming that this is the ground, okay? I know it's a certain height above the actual ground, but let's assume that it's on the ground. When I take my hand and I lift it, I start to give it energy, and it goes from 0 to something else. That is why my applied force is non-conservative. It has started to add energy to the system. If we have a block on the ground and we push it, and we give it a certain amount of kinetic energy, but there's friction, what's going to happen is that our block is going to slow down, because this friction force is taking mechanical energy out of the system. That is why it's non-conservative. Okay, so now that we understand that, if we speak about non-conservative forces, friction force, which you guys are familiar with, we rarely have air resistance, so we can do funny things. Tension force, the applied force. As soon as you see forces like those and they are doing work on the body, then you know we have non-conservative forces. Okay. There are 3 formulae that we now look at, and using this knowledge of non-conservative and conservative forces, we decide which formula we're going to use, or at least try, through a process of elimination. So if you're looking at your document, at the top right-hand corner, you're going to see this one. Now, Principle of Conservation of Mechanical Energy. The principle of conservation of mechanical energy, keyword here, conservation, is, or states, the total mechanical energy in an isolated system remains constant. You see, you guys were studying, you know your definitions, or you were reading, but I'm going to assume you were reciting it from the heart. Okay, so guys, the key word here is isolated system. And the fact is that you can only use this formula provided there are none of these non-conservative forces acting. So if there's friction, if there's an applied force, if there's tension, do not use this formula. Number one, it's not given on your formula sheet, okay, number one. But I know you guys memorize it because you know that you might need to use it, okay? And if you do use it, you'll get full marks, provided you use it in a context where there are only conservative forces acting and no non-conservative forces are doing work. On to the other two. The beauty about these two forces is that they kind of don't care what type of system we're in. Because there's always gravity, okay, so there's always going to be this Fg, this conservative force. But these two don't care if it's an isolated or, well, not isolated system, right? So, the first one is the work energy theorem as you guys learned it. But then we have what we call the work energy theorem in general. You see, the work energy theorem, if you say that the non-conservative forces are zero, you can take this formula and manipulate it to be the conservation of mechanical energy formula, okay? Where are you going to use each? Well, this is the best I can give you. You want to use this one when you know enough about the speed of the object or the velocity of the object and you know its mass, and when you know all of the forces acting on the body. Okay, if you know all of the forces, or if you know the net force, you want to use this guy. Okay, in cases where you don't know all of the forces, but you do know the non-conservative forces like the applied force, friction, so on, then you want to use this one. And please be careful. I know we don't use the sum sign. So guys, this is the symbol we use for sum. Please don't write it like this. It's different. This is EMF. It's an epsilon symbol. And this is sigma, meaning the sum. So we should have sort of said the sum of the non-conservative forces. That would have made it a bit more complete. But if you have a block and there's an applied force on the block and there's friction, then you're going to include the work done by the applied force and the work done by friction on the left-hand side of this formula. I can't see. Was that the 30 minutes? Yeah. Thank you. Okay, so that is the best I can say to you guys. If there's formulas, or if there's conservative forces that are missing, you want to use this one. If you have all of the forces or the net force, you're going to use that one. But it's really a process of elimination. Most of the time, you're going to see that you can use both, and that is why this is a horrible section to mark, because there are like 5 different options. Get comfortable with trial and error and take it from there. But if you find your first method doesn't work, be calm, guys. Leave it and try the next method. On that note, please don't cancel something before you have reattempted it. If you run out of time while trying your next option, but you've already cancelled the first one, you're not going to get any marks. So first reattempt, and once you are done reattempting and confident, then go back and draw a line through the thing that is wrong. Okay. We only have 30 minutes left, so I'm going to continue. Are there any pressing questions? Yes?
On an inclined surface, does Fg count as a non-conservative force?
No, Fg parallel would be conservative. Okay, so your components of Fg, because Fg is conservative, its components are conservative as well. Okay, I saw another hand, yes? Yes, you.
Which equation do you use when you don't have the conservative forces?
When you don't have the conservative forces, you're going to use the first two. So when you only have non-conservative forces, then you're going to use these two. Please understand, this one over here at the bottom, you use this formula when you have no non-conservative forces. So if there are no non-conservative forces, use this one. But if there are non-conservative forces, use this one or use that one. Okay. Yes.
Miss, it's not a question, but I wanted to add something.
Yes.
So, Miss, one of the formulas my tutor gave me is the formula for calculating the work done by conservative forces.
Okay.
But it's not given in the formula sheet. So he said the work done by conservative forces is calculated by the negative change in potential energy.
Oh yes. What about it? Do you want to use that formula?
Miss, can we use that formula instead of using your mechanical energy conservation?
Okay, so that one, if I'm not mistaken, is used as part of the derivation. When we are trying to go from these formulae to those ones, then we deal with that one, okay? I might be mistaken. You're talking about a non-conservative force formula, right? Non-conservative, conservative. So can you say it again?
Negative change in potential energy.
Negative change in potential energy. Yes?
Is equal to the work done by conservative forces.
Okay, yes. We use this as part of the derivation. Are you in a government school? Are you writing the government? So, okay. If there are any formulae that you see in your textbook, because I know that this is in the answer series textbook, and it may be in others where you need to perform a derivation, I'm not going to say don't use it, but please be careful because we tend to only give marks for formulae that are on the formula sheet. Okay, so this formula is used as part of this or as part of that. And so first write down one of these and then go to that if you're going to use it. Okay, it means you have a very good understanding of where the formulae come from. Okay. Alright guys, I'm going to move on to the Doppler effect. And I don't have much to say on it except, on page number 7, please cancel this. If they ask you what we use the Doppler effect for, please do not say ultrasound machines, cancel that. Okay? We do get what we call ultrasound or Doppler ultrasound machines, but it's always debated and we just don't want to do things that are debated about. You're either going to explain the blood flow meter or how we measure the heartbeat of a fetus, okay? But yeah, please cancel that. Don't use that guy. You're going to remember when families come together, it's a good thing. So if two bodies or if the observer or the source, the listener or the source are moving closer relative to each other, choose the plus sign at the top. When families move apart, it's a bad thing. Choose the negative at the bottom. Learn this off by heart and you're going to be okay. However, we have said in tests, if you are performing a calculation, please always start off by writing down the full formula. They are no longer giving you guys marks if you start off with the formula like that, for example. Okay, first write down the full formula as it is on your formula sheet. And when you are done with that, you're welcome to change it ever so slightly. We don't want you guys to manipulate formulae and make something the subject of the formula before substituting. You always sub first and then you manipulate. But in this case, if you want to change it to this, do so after you write down the formula exactly as it is on the formula sheet. Now, I don't want to say too much about this question because there's something about it that I think is a bit off, and I don't want you guys to go home and then have debates, okay? But I guess I have to mention it. You see, what confused you guys is they have an FO here, which you guys registered as observer. It should have been the frequency of the source. You see, in my opinion, I might be wrong. Okay. Because what is happening is the observer is the person who is standing stationary. And what happens is that there is this police vehicle that is moving. Okay. Now, this is what we know. If we have two bodies that are moving close or together or towards each other, then we expect that the frequency of the listener will be larger than that of the source. If we have, hey, there's lots of debates here. Okay. If we have, guys, that they are moving apart, then we expect that the frequency that is observed is going to be lower than that of the source. So here's a common mistake that some people made. Maybe your teachers are nicer than me and they won't penalize you, but they asked in question 6.2, which graph A or B shows the police car moving away from the observer? And that would be this one, B. Okay. Alright, so now that we know that it's B, we state the reason why. And the reason is not because we compare the two graphs to each other. The reason is because we compare the frequency observed or detected by the listener to what the source is truly emitting. And so in your explanation, you should have not only said that the frequency observed is lower, but you had to say lower than what. And therefore, I looked for the frequency recorded, or what the listener detected, is lower than the emitted frequency. You guys must be specific. What are we comparing here? Make sure you tell me. Most people, or a lot of people, just said the frequency is lower and they left this part out. But lower than what? Okay, what according to the Doppler effect are we comparing so that we can come to this conclusion? Be as specific as possible in your exams, please. Okay, I'm going to skip this. You guys will look through it if it is the paper that you wrote. If not, you're going to attempt it and then you're going to mark yourself. Over here we had at 6.3 a question on emission spectra. Due to time, a lot of teachers skipped this section. But it was in last year's November paper, it was in this year's provincial Gauteng paper, and so you do not want to skip emission spectra. Okay? If you've never seen it before, speak to me so that I can help you. But, and IB learners, you guys don't do this at all. If you are lost and you're wondering, what are we doing? IB, you guys don't deal with the Doppler effect. So what you guys missed is, they said, study the emission spectra A, B, and C of a distant star as observed from the Earth. Spectrum A is in the lab, and it is the reference spectrum. You see this one? That's the reference spectrum. When nothing is moving and we detect the light that is being emitted by a certain atom or a certain molecule, then this is what we're going to get. What I found most people skipped was they didn't read what was at the top. Red region, blue region. We don't give our papers in color. Okay, DBE doesn't give color. But we do give you guys guides so that you know which side is which. So when they said which spectrum indicates that the star is moving away, you guys should know that motion away is associated with redshift. And so we can see over here that this one moves towards the left and it's therefore redshifted from the original emission spectrum. They say if the blue part of the spectrum is being observed, describe the frequency and length of the light. This is actually a grade 10 question. You guys should know Roy G. Biv, red, orange, yellow, green, blue, indigo, and violet. Okay? And you should know red light has a high wavelength or long wavelength, short frequency, while blue light, I know we call it blue shifts, but it's not because the light turns blue, it's because it's shifted towards that end. So if it was green, it now appears blue. If it's blue, it now appears indigo or violet. That's a blue shift. So we know blue tends to be relative to red. It has a short wavelength and a high frequency. Okay, and based on that we would say, because it's blue shifted, high frequency, short wavelength. And that was the Doppler effect. Okay, we're almost done. We only have 20 minutes left. Are there any questions on this? Just the big thing. Sometimes, guys, because we see you guys have become comfortable with the Doppler effect. I always say to my learners, this is the easy section. You guys must know this. But the reality is we are seeing that you guys are getting comfortable. So what we do, we take your easy section and we turn it into hell. Please try the difficult problems of the easy sections. Oh, I like the Doppler effect, yes, but have you tried the hard questions? Look for the hard questions. Don't build confidence by doing the same thing over and over and over again, and just because you get it right, you think you're on track. Try the different questions. Okay. Guys, electrostatics. I don't have a lot to say on electrostatics except about how you approach the question. On the summary page, I don't know which page it is on, I didn't indicate it here. Let us see. This is on page number 8. Okay. What I need you guys to please understand for the future is that if we are looking at electrostatics, this formula for force and these two formulae for the electric field are scalar formulae. Okay. They are scalar formulae, which means they only give you the magnitude of the force and the magnitude of the field. F is for force. F has been for force since Newton's laws. So F in electrostatics is for force, not the field. Okay? F is not for field, F is for force. And even in electrostatics, force is measured in newtons. Okay? If we're looking at the electric field, on the other hand, it is given the symbol E and it is measured in newtons per coulomb. So you're going to see on my summary page, I don't just give you the formulae and the definitions, I also tell you what we measure them in so that you know your unit of measurement as well. This is one unit of measurement that for some reason everybody forgets and leaves out. So I had a lot of learners telling me that the electric field is measured in coulomb, or it's measured in newtons, or whatever they could think of at the point. Okay. So if these formulae only give us magnitude, it means we do not, grade 12s, we do not substitute negatives into these formulae. If the charge is negative, leave that negative alone. Leave the nature of the charge alone. You only plug in the positive version of the charge because that is its magnitude. Over here, when you substitute in these things, when you start substitute over here and there, and even if I first give you the force or first give you the electric field, when you sub into these formulae, leave the negatives alone because these are scalar formulae. So how do I determine the direction if this does not give me the direction? You determine the direction of the force by saying, is the force an attractive force or a repulsive force? And then you determine the direction. If we're looking at electric fields and I say to you, what is the direction? We determine the direction by making use of the definition of an electric field, which speaks about a positive point charge. So, how do we find its direction? We say, where will a positive test charge move? That is how you're going to determine the direction of the electric field, but not from the formula. If you sub in the formula and you get a negative, it means you've done something wrong. These formulae only generate positives because we don't put negatives into them. So looking at this question that you guys got, it said, 2-point charges A and B are placed 3 meters apart. The charge on A is positive 6 coulomb and the charge on B is negative 3, times 10 to the negative 6 coulomb. So, looking at that, they were very kind and they put the charges in coulomb for you. Please remember, if they didn't, you need to know this off by heart and be able to do conversions or they're going to penalize you. Charge is measured in coulomb. If we're talking about distance, distance is measured in meters. Please perform your conversions. They then say define the term electric field at a point. Most of you define an electric field and you don't get your marks. Electric field at a point is the electrostatic force per unit positive charge placed at that point. And we can see this in the formula. Electric field is force per unit charge. IB uses the small q, which I actually like, because then you know it's the test charge, the positive little test charge. But DBE uses a capital Q, and you need to know this is the test charge. So you attach your definition to a formula to help you to remember it. Now in the next question they said, calculate the net electric field at point P. What you guys must do, so if you did not do this, this is why things are not working. The first thing you must do is draw a diagram for yourself. A vector diagram, a free body diagram, so that you can determine direction. We have point P over here. So remember, this is about electric fields. We only have 10 minutes left, but we'll get there. There's point P. The question is about the net electric field at point P. So how do we determine the direction of the electric fields? Number one, we're going to cover the sky. We're going to say, electric field is defined in terms of a positive test charge, and we put our little positive test charge over there at P. Now we say, where will this free test charge move as a result of A? A is positive, test charge is positive, so what is A going to do to the test charge? Repel it, it's going to push it away. So I know, and I draw a little diagram for myself showing that the electric field due to A is going to be towards the right. When I'm done with that, I'm now going to cover A. I don't need it anymore. I'm done with that guy. I look at B. B is negative. What will B do to the positive test charge? Attract it. So as a result of B, I now go and I show the electric field due to B is going to be that way. Okay, that's the first thing you do. If you did not do this, that is why things are becoming a little bit messy. Now, they asked for the net electric field. You see, all of these formulae are scalar formulae, but you're going to see at the top here, I said, in electrostatics we have some vectors. Vectors apply when we see the term net. We're almost done, guys. I know you're ready, you're hungry, you just want to eat, but in 5 minutes we're going to be done. Okay, so stay with me. Guys, net is about vectors. Okay, so that is why we drew a diagram, and now that we are done drawing the diagram, we write down the formula for electric field. We calculate the electric field due to, I think this is A, let's just make sure. Yes, it is. This over here that's written on the exam or marking guidelines is this. You see, I look at this at the top, it's to the right, so I wrote that down. I did not get that from subbing into the formula. I got this part by asking myself, what will happen to a positive test charge? When I'm done with that, I determine the electric field due to the other charge, which is B. And please note that when I substitute into this formula, this is positive because it is only magnitude. These are scalar formulae, so you don't put negatives into it, okay? Out comes a positive answer in newtons per coulomb. So where does this thing come from? Which isn't for marks right now, by the way, but where does this come from? It comes from this pretty diagram that we drew at the top, showing that the electric field due to B is towards the left. All of the work so far has been scalar work. Everything we did at the top was about scalars. As soon as we then need to determine the net electric field, we remember we are adding vectors. Because a field has both magnitude and direction. I choose a direction as positive, and then I say, since I'm choosing the right as positive, I'm going to take the electric field of A and subtract the electric field of B. We plug it in, we get a negative answer. And given that I chose right as positive, if I'm getting a negative answer, it means left. Okay, and you make sure that when you answer this question, you write down the magnitude as well as the direction. Now these are grade 11 questions, and when you guys get them wrong, we shame you for it, and I feel bad when I do so. Just because it was taught in grade 11 doesn't mean it was easy. Just because you've seen it 100 times doesn't mean that you suddenly understand. There are certain misconceptions that you guys have, certain questions that you have not been answered, and you need to reach out to someone to answer those questions for you. Whether it be me or somebody else, you have a group of physicists all around you guys. There's about 150 people in here. Each person here specializes in at least one of the topics. And if you guys collaborate, you'll find someone who has mastered this guy that maybe you have not mastered, and they'll be able to teach it to you. Okay. Now the last question said a proton is placed at point P. No, it's not the last question. It's going to be the last question for us. Calculate the magnitude of the initial acceleration of the proton if the mass of the proton is this amount. Okay. Guys, first mistake you made. What I just said about these formulae is that they are scalar formulae. If you also chose right to be positive, you got a negative answer. And you know what some of you did? You plugged negative into this formula. It's a scalar formula, so we don't put the negative in. We plug in the magnitude, we plug in the mass of the proton. Out comes a force. Remember, force or net force is mass times acceleration according to Newton's law. And out we get an answer. Okay. Are there any questions that I can answer at this point? We're tired now. We're tired and we're hungry and we want to sleep. Yes. So we don't have questions anymore. Okay. Alright, if there are no questions, I can at least do the last one. They say if an electron was placed at point P, how would the acceleration of the electron compare to the proton? Okay. Guys, if you take a look at your table of constants, you're going to see the mass of an electron. It is smaller than the mass of a proton. You see in front of me, I have a tiny little electron and I have a big bus. I'm going to punch the electron and then I'm going to punch the bus. Do you think the bus is going to move? I'm using the same amount of force, but because the bus is so large, it doesn't move. And because the proton or electron is so tiny, it's going to move. So this question is out of 2 marks, which means I'm looking for 2 things. Acceleration is a vector, which means what? Magnitude and direction. Most people only answered one of the components, alright? The electron, being smaller, will have a larger acceleration. But because it has the opposite charge, it will move in the opposite direction compared to the proton, and that is your 2nd mark. Okay, there's a lot more that I would have wanted to say, like for example, how to draw these field lines that you guys mess up so often, or how to deconstruct these questions, but we've unfortunately almost run out of time. Let's just see if there's anything very important. A very small thing I want to point out, guys. If you are looking at questions, we're almost done. If you are looking at questions on the photoelectric effect, if you leave out max, you're not going to get your formula mark. Okay? You copy down formulae exactly as they are on the formula sheet, or you lose marks. Okay? I want you guys to think of this formula in this way. If we are talking about EK max, it's the maximum energy, kinetic energy, that an electron may have. If learners were like this, which you guys are not, if a learner entering my class was blank and had no knowledge, which is not true, and I as the teacher was the only source of knowledge, and now I have 5 learners in my class that are completely blank, and their only source of knowledge is me. And I can give them a 75% based on my knowledge. Right? What would happen is Some learners would get 73%. Some would get 20%. Some would get 40%. But based on the knowledge that I have, the maximum that they can have is 75%. Okay, fortunately it doesn't work that way. So if I'm a 75% teacher, you guys can reach out to other humans and get answers from them. But you see, the reason why this max is important is because it is literally the maximum that an electron may get. But it can have lower amounts of kinetic energy. So please don't leave that out. Okay. I am going to stop with the content here, but just something I want to point out to you guys. I've already mentioned it, but I'm going to say it again. If we are looking at all of these hundreds of topics that you guys need to study, mechanics, wave, sound, light, electricity, magnetism, matter and materials, I don't need you guys to put your hands up, but I want you to think in your heads. There's at least one topic here that you love and you appreciate, and it's just the best thing in the world for you. The chance that the person sitting next to you loves the same topic is actually very low. Okay. So guys, you have the opportunity here to collaborate. You have the opportunity to sit together and tackle questions. There are a lot of talented people who are sitting among you. Please network, ask questions, and then just a reminder, if you're looking for multiple choice questions, if you're looking for more practice problems, so I have documents where we take all of the topics from past papers and put them together. If you don't have documents like that, please just send me an email. I won't spam you. I don't want anything from you, I promise. I will just send you the documents so that you have something to work with. We are now preparing for exams, which means we need to know how to write exams. Okay, thank you guys. I hope that supper is going to be good. You guys are very tired and hungry.